We can find the variance of the exponential distribution with rate parameter lambda using the computing formula, and we found that e of x is 1 over lambda. Now it's worth pointing out that since we found the expected value of x is 1 over lambda, this actually corresponds to the value of the improper integral. So to find the variance, we need the expected value of x squared, which we can set up as, we'll use integration by parts. We'll let u be x squared, dv be lambda e to minus lambda x dx. We'll integrate to get v, we'll differentiate to get du, and so this integral becomes. Now this first term, if we evaluate it between 0 and positive infinity, we get 0. This second term, let's clean this up a little bit so we can factor out that negative 2. And this looks an awful lot like our integral for the expected value. So we can get it to be the integral for the expected value if we put in a lambda, as long as we take out a lambda. And so we know the value of this integral is going to be 1 over lambda, and so that gives us the expected value of x squared, 2 over lambda squared. And so this means that our variance is going to be 1 over lambda squared. And finally, the square of the standard deviation is the variance, so the standard deviation itself is going to be 1 over lambda. And note that this means that for the exponential distribution, the mean and the standard deviation are the same. Now, this puts us in a rather odd position because the standard deviation is the same size as the mean, and remember, for the exponential distribution, nothing can be less than 0. So let's consider an exponential distribution with lambda equals 1/10. Let's compare the actual probability of being within 2 standard deviations of the mean with the lower bound established by Chebyshev's theorem. So the mean is the reciprocal of the rate parameter, that's going to be 10. The standard deviation will be the same, and so the probability of being within 2 standard deviations, well, in order to be within 2 standard deviations of the mean, we have to be in the interval from, or doing the arithmetic, that puts us between minus 10 and 30. But remember, the probability that x is negative is going to be 0, so we can ignore the negative portion of the interval. And so this probability is the integral from 0 to 30 of our exponential distribution, which will be the probability form of Chebyshev's theorem claims that if you're within k standard deviations of the mean, that probability exceeds 1 over 1 minus k squared. And so substituting in those values, we get, so the probability that we're in that interval is at least 0.75. And in fact, we found that it exceeds 99%. So Chebyshev's gives us a substantial underestimate. But remember, you get what you paid for. Chebyshev's is very easy to apply and works for any distribution, whereas here we had to do some integration and know some more things about our distribution to get this answer.